Mapping out the timeline of the universe has been one of the greatest achievements of 20th century astrophysics. And quite a bit's been said about the Big Bang in a lot of astronomy outreach talks, including at the AstroTours. But there's a period of time in the universe's history, after the universe became transparent to light for the very first time, and before it became populated with stars, galaxies, and all the things that we know today, called the Dark Ages of the universe. And this age still remains very mysterious to astronomers today. Tonight, graduate student Jielai Zhang will explore the secrets of this dark age of the universe. Jielai got her bachelor's degree in physics, mathematics, and aeronautical engineering at the University of Sydney, and now works here, where she images some of the faintest galaxies in the universe. Take it away, Jielai.
Hi everyone, my name is Jielai, as Charles already said. I'm a graduate student here, and one thing lots of people like to ask is, why do you study astronomy? Well, let me tell you why I'm studying astronomy. Ever since I was really little, I've always wanted to know the origin of things. Where did that flower come from? There was no flower there before. Well, when I found out it came from a seed, then I started thinking, where did the seed come from? Oh, okay, there was another flower. Well, where did the first one come from? Where did life come from in the first place? Before life, there was, of course, the Earth. Before Earth, the solar system and our sun. Before the sun, the galaxy. And before galaxies, all galaxies in the universe. And it turns out that turned into a PhD project, so that's kind of where I'm at right now. And don't get me started on the whole entire universe. When you look up into the skies, we've been doing this for centuries, and stars and all the twinkling lights above us have been part of our culture throughout all of history, all the way up until the present moments, with cosmic candies. When I was growing up, I loved the Milky Way. And so these questions about what are the origins of things, where did things come from, they've been asked in all sorts of different ways throughout history. And in a way, that question boils down to, where did all this complex stuff, this complexity in the universe, how did that all arise? How in the world, how in the universe did it come about? Was it always like this? Stars and galaxies? To answer this question, let's go right back to the beginning. Right back to the beginning, it turns out that the clues to all our questions are written in the skies. In the 1920s, Edwin Hubble made a very important observation of galaxies in our universe. He made observations of lots of galaxies, some closer, some more distant, and he found that every single galaxy, except the ones right up close to us, they're all moving away. Furthermore, he observed that, see these further, the yellow dot is where we are, the further the galaxies are away from us. These galaxies, they were running away from us faster than the ones slightly closer. What was going on? What can possibly explain what we now call Hubble's law? Well, it turns out the answer is that the universe is expanding. Okay, if the universe is expanding, it kind of makes sense that everything is, moving further away. But does it make sense that further away galaxies are moving away faster? Let's take a deeper look at this for a minute. By using an analogy to bread. It's not breakfast time, but oh well. So we're going to represent a portion of the universe with this loaf of bread. And the raisins in this loaf of bread represent the galaxies in the universe. The expansion of the universe is represented by the rising of the bread. So in this case, the bread has expanded to twice its size. And you can see, if we're that galaxy that's in the middle of all the other galaxies, right? Oh, I have a stick. That galaxy right there, then The closer galaxies, for example, the one that's 1 centimeter away, after the bread has got to twice its size, it's moved twice as far away. But twice 1 is 2. That's only 1 centimeter further. But if you're further away, twice that is a much bigger number. And so in the same amount of time, these raisin galaxies have traveled further away. Thus, they are moving away faster. The beautiful thing about explaining Hubble's law with the expansion of the universe is that if you were living on any other raisin, you would observe the same patterns. Everything would be moving away from you, and the further away it is, the faster it will be moving away from you. So we've got that down pat. And I just want to add, this is not the only evidence for the fact that our universe is expanding. There's a whole bunch more, and it's one of the most believed in and one of the most evidenced theories in science, which is kind of amazing because this happened 14 billion years ago. All right, so written in the skies is the history and evolution of how our universe began. Because if we take back the expansion of the universe to its take it to the extreme, we know if it's moving apart now, it was closer together in the past. The further back in the past you go, the closer everything is. At some point, it's got to be on top of each other. We call that point the Big Bang. With the Big Bang, which is the state of extreme heat and extreme density, the universe began with all its contents, including electrons and protons and neutrons. These are the building blocks of all matter. And also, if you guys are standing back there are seats around. I will not find it rude at all if you just kind of try and move in. That's fine. I don't want you to sit there for a whole hour. So these electrons, protons, and neutrons, the building blocks of all matter. And so that was an extremely simple state. All you had was whizzing around like crazy electrons, protons, and neutrons. No galaxies, no stars. It was kind of the same everywhere. What happened from there onwards such that there is so much complexity? I like cats. Do you like cats? Some people don't like cats. How did we get so much complexity in the world today? Let's start at the point of the Big Bang. And let me reintroduce to you electron. Miss Electron over here is negatively charged. What that means is Miss Electron is extremely, extremely attracted to positively charged things, such as Mr. Proton. And so whenever the electron and the proton get anywhere near each other, they're going to feel a sense of attraction, and they're going to just attach. You pass your reading test. However, unluckily for the electron and proton, as we were saying, this is early on in the universe, a hot, dense plasma soup. There's a lot of energetic light around. These lights, or photons as we can call them, will come around and smash into the electron and proton, giving all of its energy to the electron and rip the electron off the proton. This process is called ionization. Now, ionization, that word we're going to use over and over again. So everybody remember ionization, ripping the electron off. The electron's kind of sad, but it's okay. There's plenty of protons around. So the very next one it comes into contact with, it'll just reattach itself only to be ripped away again. And again. And again. These poor old electrons. Meanwhile, while the electrons are not having so much luck in this hot, dense plasma soup because of all this radiation, neutrons were having more luck. Now let me introduce to you the neutron. Neutrons are neutral, so then they're not attracted in the same way to these protons. Even if they're close to each other, they're not going to go kablump. However, the universe was hot, it was dense, there was a lot of these running around. And so at some point, one of these neutrons is going to whoosh so close and go so close to the proton that at some point, something magical happens. The magical thing that happened is called the strong force. The strong force is so named because it is exceedingly strong. It's, I know, we're so clever. It's 137 times stronger than the attraction of positive and negative things. And it's 1, 0, oh, I should do it the other way because you're all face, anyway, 1, 0, 0, 0, 0 with 39 zeros after it, times stronger than the force of gravity. There you go, very strong. It's so strong that sometimes when you have 2 neutrons and 2 protons, even though the protons are both positive and they want to get away from each other, the neutron and the proton bond, this strong force, can keep all of that together if they just get close enough. This particular thing here with 2 neutrons, 2 protons is called a helium helium atom. The helium atom in everyday life, you know, the one that makes your voice go really, really high? Helium normally would have 2 electrons attached to it, and that would make it a neutral atom. But right now, electrons they're not having very much luck, as you know, I repeatedly said. Not all the protons, however, will be combined into making these heliums. There'll be a whole bunch of protons running around by themselves. A single proton is also called a hydrogen atom. However, again, in everyday life, these hydrogen atoms usually have an electron attached, and that would be neutral and not ionized. All this happened during that hot plasma stage right after the Big Bang. And the Big Bang was able to make 73% hydrogen, 25% helium, and 2% lithium and beryllium. You might ask, hold on, I thought there was a few more stuff than this. Where did it, what? Only hydrogen, helium, lithium, and beryllium? There's got to be more. And I have a wonderful song to illustrate all the elements of the periodic table. It's really, really cute, so I have to show this to you. Wait, where's the sound?
You'll just have to sing it.
Oh, I just have to sing. I might sing once in today's lecture, but I'm so bad you don't want me to sing for 2 minutes. Is that good? Okay. It's as high as possible. There we go. That's what we breathe. I know. I knew that was going to get a laugh. Okay. I'll stop it there. You can search the periodic table song on YouTube, and this is what you'll get. I can watch this for hours, but let's move on with the talk. So there are 118 elements in the periodic table. That's a lot of elements. That's almost as much Pokemons as there are when the Pokemons first came out. There was 150 of those. But anyway, this huge array of complex elements. What? They're not made at the beginning when everything was made. Where did it all come from? How do you turn hydrogens and heliums into such an array of elements on this table? For example, there's carbon. We're made of carbon. Oxygen, we're breathing oxygen. It's got to come from somewhere. Where? Stars. We'll get and that is where we're going to get to eventually. So the question is, how do I get from this to this? Let's continue our story with poor old electron, and we'll find out. So, as we were saying, these electrons, not so much luck. And guess what? You think you've had your heart broken too many times? 380,000 years. This was happening to the electron for 380,000 years after the Big Bang. And one fateful day, 380,000 years later, this photon comes along, and it just left the electron alone. It just went off. The electron was really happy, kind of ecstatic. Did this really happen to me? So I guess, how did that happen? What makes photons able to ionize these elements and rip the electron off? And why, 380,000 years after the Big Bang, the electrons were finally safe? To answer that question, let's delve into how photons, exactly how these photon things work. So a photon, as we were saying, is a particle of light. Light has a wavelength. The wavelength of light is represented in this diagram by the distance between the two peaks of the squiggle. So that bit between the red lines. The longer the wavelength, the lower the energy of the photon. So for example, back at the beginning, during the hot phase of the Big Bang, there would be a range of different wavelengths and energied photons running around. So some of these will be higher energy and some lower energy. Which one's higher and which one's lower? Higher up the top? Yeah. All right, you guys have got this. And so the higher energy photons are up the top because they have shorter wavelength and they're more energetic. And in order to have enough energy to rip off the electron, you needed to be shorter than a certain wavelength. So these were the photons ionizing the atoms in the early universe. What happened? Where did they go? So we gotta take our head back to remembering how. Ooh, we got some action going on here. So yeah, exactly. Remember we were saying that the universe is expanding right now, and it expanded from something that was dense and hot. Well, it was expanding back then too, all the way from the beginning. It's been expanding forever. And like this, as the photons are traveling through space, as space expands, since the photons are in it, they're getting expanded too, and they stretch to longer wavelengths and become less energetic. So pretty much 380,000 years later, all the photons that were there at the beginning got cooler and stretched and less energetic, so that none of these photons had enough energy to ionize hydrogens or heliums anymore. And that's why all the stuff in the universe, all the hydrogens and heliums, all that gas can finally become neutral. This process of the electrons combining onto the positive friends is called recombination. This is another word that will come up again and again. Recombination, things becoming neutral. Okay, Now they're all neutral, and they're floating around. There's no more positive, negative things going on. But now that there's no positive, negative things going on, and everything's neutral, gravity firmly shook the hands of hydrogens and heliums. And gravity, being the weakest force, slowly started to collect material together where it's slightly more dense. And that's how the first dense stuff started to form from about this time. It turns out that this was all that happened for the next 400 million years. I guess you can call this the childhood of the universe. And yeah, my mom told me I was home too long. Well, I think I'm doing pretty good. So I said this whole idea of gravity slowly pulling things together and forming structures. What do I mean structures? And what does that look like? Let me show you a movie, because they're the best way to visualize things. And this time, there's no sound, so I don't have to worry about. Okay. So the slightly brighter places are slight concentrations, slightly more dense regions of hydrogen and helium. And over time, those regions got more dense. And the less dense regions will material float out of them and into the most dense regions. And the structure that we talk about, the structure is all these webby, spider webby looking things. And that's how gravity works. Slowly, over a really long time, pulling things together. Do we need to see that again? Yeah, it's pretty, isn't it? You can, all of the things I'm showing you today, you can find, they're freely available online. So you can search, well, reopen. Okay. To find this one, it's the Millennium Simulations. You can show all your friends when you go home. So you can see material slowly collecting together, the dense regions becoming more dense, and thus the growth of structure. This is actually really difficult. And I don't do simulations, but if you want to know how difficult it is, you can talk to Charles after. He does simulations, not of this, but of other things. Okay. So that was gravity at work. To give you a sense of how big of a region was I showing you in that video, I took a slice of the video, and here it is. In this picture, the size of a galaxy is that tiny little black dot above the O of the OV. So I'm showing you a humongous patch of space. We're not talking about a bright blob is a star. A bright blob in here is a whole galaxy or a cluster of galaxies. And so yeah, this slice is taken when the universe is 200 million years old. So this is a simulated image of what the universe would look like when it's 200 million years old. This sits it right in the middle of that 400 million years when the universe was just doing gravity and nothing else. Actually, I lied. I said this is what the universe would look like when it's 200 million years old. Look like is misleading. The reason it's misleading is because if you were actually to borrow a time machine from that guy with the hat, what's his name? The doctor. Thank you. If you were to borrow a time machine from the doctor and plonk yourself right in the middle of this universe at this time, and you take a look around, you would see this. I did not make a mistake. This is right. You would see absolutely nothing, as as he said up the front. You might think you've gone blind, but you haven't. You look in every direction, there's nothing. The reason for that is because there's no light around. There's no light that your eyes can see. There is no visible light. There's no stars. There's no galaxies. So yeah, there's no light. There's just happy neutral hydrogens and heliums floating around, sometimes collecting together because of gravity. So yeah, 400 million years of just slowly drifting closer to other gas. And this period is called the cosmic dark ages, something not very often talked about because we know so little about it. The cosmic dark ages, not just a metaphor. It's not just saying, oh, that's when the universe was boring. It was literally dark. What? Yeah. So the universe went from hot plasma to the dark ages after 0.4 million years. And then it just stayed that way for another 400 million years. Kind of dramatic. I'm going to be really exciting, so for 400 million years, I'm going to sit here and make you wait. That's how I think of it. And it's actually true. Something extremely dramatic had to happen in order for there to be light that we can see, in order for us to see stars far away, see galaxies far away. Something dramatic had to happen. Let me explain why it was so dramatic. Again, we're going to plonk ourselves with a telescope this time, 200 million year old universe, and take a look around. Dark, right? But what if suddenly, far, far away, that's many, many, many galaxies away, a star turns on right there at the red cross? Will we be able to see it without telescope? Well, I'm hearing a lot of no's. Why is that? Light would have to get. What if we waited so there was time for wait for however long it takes light to travel? Would we then see it? Yes? No? No.
Too much stuff in between.
Too much stuff in between. Yep.
The waves would be elongated to the point probably beyond too low of a frequency for us.
The waves get elongated, and so we can't see it with our eyes.
We would probably need something like microwave or
Maybe microwaves. All right. That's great. I can see you guys are really thinking. It took me a while to get my head around this. And I was going to say a simpler explanation. But since you guys are so on top of it, I'm going to give you the full explanation. All right. So this star would be giving out light of all different wavelengths, all different energies. And since it's so far away, while the light is traveling through space, space would expand and stretch, so it would go to shorter wavelengths. So if we were to look at this star at shorter wavelengths, sure, we would see it. But what about, but there's something extremely important. If we look at it in the optical wavelength, even if the light from the star had just enough stretching to make them visible light, we would not see that because of something that you said. There's too much stuff in between. There's all this neutral hydrogen around. And so if the light was originally energetic enough before it got stretched, it was energetic enough to drive these electrons crazy and rip them off the protons, ionizing instead of traveling on into space. And so, absolutely right. No, our telescope would not see the visible light. Can we see visible light from far away in today's universe? Yeah. Well, yeah, it's the light traveling from far away that's taken the time to reach our telescopes and our eyes when we go out at night, which hopefully when we go out tonight, we'll be able to see something. But this is an example showing that yes, indeed, we are detecting visible light from faraway sources, like galaxies. This is the Hubble Deep Field, and each one of these dots is a galaxy, millions, billions of light years away. Where did all the neutral hydrogen go? And this was the dramatic thing. Either all the hydrogen just poof, disappeared, or they got eaten up by stars and galaxies, and so they're just not in the space between galaxies, or they somehow got ionized. Because ionized heliums and hydrogens, well, they don't eat up any more light. And so it would be transparent to the visible light. I should have put up this one. Where did all the neutral hydrogen go? So to answer this question, we need a way to differentiate whether the neutral hydrogen is just, whether the hydrogen is just not there, or if it's ionized. And it turns out there's a way to do this. Ionized hydrogen is extremely energetic. And so these energetic particles, as they're flying around, turns out will emit X-rays. So if we can see a whole bunch of X-rays, then we can say, oh, it's there. It's just ionized. This is a picture of another picture with some galaxies. And then we're going to put on our X-ray goggles. And voila. Lots of X-ray emission. Lots of gas. It's just ionized. And this ionization, re-ionization of the universe is the dramatic thing that happened. The whole entire universe had to be re-ionized. And this process of re-ionization is called the epoch of re-ionization. And it took us out of the dark ages and into light. How did that happen? We need sources of light that are energetic enough to ionize hydrogen and helium. Things we know that can do that: stars, galaxies, bright things. But so far in the early universe, during the dark ages, none of that. How did it happen? The current consensus is that the very first bright objects that formed were stars. So these stars would form so this gravity at work, taking 400 million years to do its thing, would bring gas together. Gravity would take over, and then poof, everything got so tight together, it becomes a star. And these stars, well, actually, they're not like any stars that we know in today's universe. And the reason for that is, in order for gravity to put things together and for stuff to shrink, it can't be hot. If it's hot, it'll be like, oh, I'm hot, I don't really want to shrink. And so in order for gas to condense into a really dense form, you need to let go of some of that energy so that it can become cool. In today's universe, that cooling mechanism is aided by carbons and oxygens and things that were just not there yet in the early universe. So these stars had to be really exotic and strange, and probably bigger because they needed more material and therefore more gravity pushing it together in order to condense. Therefore, it's a more massive star that's going to form. We call these exotic stars population 3 stars. We haven't seen them yet. This is a simulation of what a population 3 cluster might look like. So these population 3 stars, in the centers of these stars, they'll get really dense, really hot. And we all know what dense, hot things do, right? They smash neutrons into protons, and then the strong force takes over, and you can form larger atoms. In the centers of stars, as somebody already said at the beginning of the lecture, is where what astronomers call heavier elements were formed. elements like carbon in us, and elements like silicon, magnesium, and all of that. So that's where that came from. But for this talk, the super exciting thing is also the fact that these stars would be releasing a lot of energy in the form of light into their surroundings and ionizing their surroundings. There they come back again. These stars are forming clusters, and from the stars there'll be all this ionizing photons coming out, but only ionizing a localized region. There's only enough photons from these stars to ionize localized regions. So around a cluster, there'll be a bubble of ionized hydrogen and helium. Around some other clusters, same thing. Then the stars run out of fuel. When they run out of fuel, they just die. No more photons coming out. If there are no more photons coming out, then eventually these negatively charged electrons will happily pop back together with their protons, and everything would go back to neutral again. If that was all that happened, well, that can't have been, because we have stars and galaxies today, and the universe is ionized. So what happened after that? Well, it turns out that after these stars, after they die, several exciting things can happen. Supernovas and black holes. Whoa, I love those. And actually, Charles works on that. Supernovas. Supernovas are exciting because all the carbon and silicon and magnesium that was formed inside the star, when the star goes supernova, it blows that material out into the surroundings, enriching it for the next generation of whatever it is that forms. For example, humans. That's great. But if this was a scenario, the ionization of the universe, the reionization of the universe, would not happen. This is where black holes come in. This is a picture with the black hole. This is an artist impression with the black hole in the center, and the surrounding is gas. So this is not a galaxy. I know it kind of looks like a galaxy because it's a disk, but this is an artist impression of a black hole with gas around it. Since the black hole has all its mass, that's the same as like from the star, then all that mass, all that gravity will continue to pull things in from its surroundings. It will continue collecting material, or as you will hear in news and things like that, accreting material. So the black hole will continue accreting material from its surroundings. And because there's so much mass there and there's more and more mass going in, the accretion can become really fast. And that accretion becoming fast will mean that the surroundings can get really hot. It can get really dense. So hot and dense that the accreting material itself can start releasing energetic photons. And so the ionization of the universe, even after the star has died, can continue. There we go. I'm really glad you guys are laughing at it. I was a little worried it was going to be too corny. Okay, so the question of whether it's mainly stars or mainly these black hole accretion disks, thank you, are more responsible for ionizing the universe, like which one is more responsible, we don't actually know. It's one of the open questions about the epoch of reionization. What does reionization look like as it progresses? Here's another movie done by one of our own astronomers here at UofT, Marcelo Alvarez. I heard that his girlfriend is here. If I said his name wrong, I'm really sorry. Okay, she's not here. This is a video showing what reionization can look like as it progresses. The black opaque regions are where the universe is neutral, and the blue transparent bubbles that are forming around particularly dense regions are where the ionization is growing out and expanding into the neutral medium. The simulation, we know actually that around 400 million years after the Big Bang, the universe was still neutral. And then about 1,000 million years after the Big Bang, over a period of 600 million years, the universe slowly became neutral. Patches at first, as you saw, and then later the whole thing. The whole thing became Marcelo did this while he was still at Stanford. And then the whole universe became transparent. We don't really know, again, if it's stars or these black holes, but it's one of them, and we're going to figure it out sometime. But since, in honor of the universe becoming transparent, so that we can see everything clearly, let me replay the video with the inspirational music of Johnny Nash. So here we go. Oh, that's the wrong song. No. There we go. Yay. Oh, what? That's Frozen. It's a great movie if you Now you all know what I listen to in my spare time. That's right. Okay, here we go. The epic journey of the universe with inspirational music. Doesn't that make you feel good? Okay. So, as I said, we know very little about the dark ages and how it transitioned from dark to bright. All the stuff I've told you, the star formation, turn into black holes, accretion, the universe becoming what it looks like as the universe becomes ionized. It was all simulated. However, we do absolutely know for sure that the universe was neutral. It was simple with just hydrogens and heliums, a little bit of lithium and beryllium, and now it's ionized. And it has all the complexity that at least me, every night when I go to bed and wake up, fill my brain with awe and amazement. Or that everything ionized and complicated. And this process of going from simple to the beginning of complexity happened during that epoch of reionization, 600 million years. Understanding how the epoch of reionization progressed and how that affected the way galaxies formed, the way it affected how stars formed, is the key to understanding the beginnings, the seeds, and the progression of the formation of complexity in the universe. And it is those questions that we want to be able to answer. We've done it in simulations, in theory, and often this is how science progresses. Sometimes theory runs ahead of observations or experiments, like in this case. Sometimes it's the other way around. But the great thing is, the theorists, they've had a party. Now, observers and experimentalists, we're coming right back at them, because there's a whole lot of future work on the epoch of reionization and the end of the Dark Ages. James Webb Space Telescope. I'll just quickly go through two exciting international collaborations that's going to actually observe that period. James Webb Space Telescope, this is a real-life model of something that's going to be launched into space. Imagine that, it's huge. The mirrors are 6.5 meters across. I'm not exactly sure how they're going to do that, but they are. And it will be done in 2018. This is a picture. My supervisor is Bob Abraham is on the collaboration, and this is a picture he got sent about a week and a half ago of all the instruments that's actually going to collect the photons that traveled for billions of years from the beginning of the universe, so that we can take a peek at the first stars and galaxies. Those guys. Not too fancy looking, I know, but I'm kind of glad, because if they spend all the money on making it fancy looking, well, was it worth it? Because nobody's going to be looking at it in space. So that's good. All that needs to be done now for the launch in 2018 is a solar shield, so that we're not looking at the sun, that's bright, so we can look at the distance past, and then a system-wide integrated testing of the whole thing in cryogenic, spacey conditions, so we can know for sure it will work. Second crazy experiment or observation we're going to do is with the square kilometer array. This is a radio telescope, and it will begin building in 2018. It is going to not look at the first light objects. It will look at the neutral hydrogen and hydrogen, just the hydrogen. It will look at the neutral hydrogen itself. What did structures look like during that period of reionization? Clumpy, galaxy-like, not so much. How did it all happen? And find out how such structures can influence the formation and evolution of galaxies. This one, not going to be launched into space because there's thousands of dishes. This is an artist impression. And it's going to be built over 2 continents, South Africa and Western Australia, so in South Africa and Australia. This guy involves collaboration of 10 different countries, and it's all built in the desert where there's nobody around. So it's really, really hard. So now, coming to the end of my talk, I can tell you that you understand these questions about reionization and the Dark Ages as much as any astronomer does. And you're asking the same questions that any astronomers are asking, the questions that we're asking at the frontiers of science. I think that's amazing, and that's another reason why I love astronomy. In a short hour, you can come to grasp the most complex ideas that we're just grappling with every day. It's not that crazy. Just electrons being sad. Okay. And now, all we're waiting for is for the instruments and the telescopes to get ready, go out there and observe it. I'm excited. Are you? Thank you.
We have a minute or two for a few questions.
Yep.
So I remember you saying about the generation 3, basically the matter of 3 stars, and it's doing that simulation. So And I remember from previous talks about similar things about the lack of carbon and oxygen, how they can't form stars the way they form now. So I'm guessing, based on simulations, is it like something that's kind of possible, or are there like possible mechanisms already discovered of how the first generation of stars could form and what they would look like and like how they behave and such?
Yeah, that's a great question. The mystery of the very first stars, these population 3 stars. Based on our simulations today, so as you're correctly saying that the main problem is that these carbons and other heavier elements aren't there, and the main role they play is cooling the gas. And so they're not there to cool the gas. All we need is another method to cool the gas. It turns out there are other ways the gas can cool. For example, with hydrogen, it can also radiate away some energy. It's just a lot slower. And so that's why in the simulations, all the stars that are able to come together and make a star, they're a lot bigger and more massive. So it works, and it looks bigger in the simulations. Mm-hmm. Are you gonna pick? Okay. Yes.
Yeah. So during the Dark Ages, so what was the matter density there? Is it like 1 atmosphere, or is it like really thin, or what was it?
Wow, you've stumped me there. Does any of my fellow astronomers know? So what's the density? Redshift, like let's say 14. 1,000 times as dense as the average universe now. What's the?
Like 10 hydrogen atoms per cubic meter.
Okay,
Cubic
so,
centimeter.
all right. In 1 meter cube, only 8 atoms. Not an atmosphere at all. Yeah. So it's nothing like our Earth where we have lots of air to breathe. It's more like it's more like space, but slightly denser than space today. Thank you for your help. This is how science also works. It's not like one person has all the answers. I bug people every day, all the time. There was, yep.
I don't know what happened when you said the universe cooled off there in the first 200 million years, or whatever, the 400 million years. Where did all that heat go?
So as the universe expanded, whatever energy there was to begin with had to be in a larger volume. And so the energy in each volume got less.
Is that the background radiation now? Is that what
Yeah, and remember all those lights that were giving the electrons trouble? Well, those lights got stretched, and that light is what we observe as the cosmic microwave background. Yep.
Okay, I think this is just, I guess, a basic physics question. But I wrote, what's the relationship between the universe cooling and the wavelength of the photons? So is it just that the particles, so when it's heated, the particles are moving faster? So they're slowing down?
Yeah.
As the universe
What
is
do I mean?
expanding?
Particles and wavelength? That doesn't even make sense. What do I mean? Is that?
Well, the way that I did my master's in biology, so I'm not as familiar with it, but the way that I understand it is when things are hotter, the particles are moving faster.
Yep. So that's exactly right. As the universe expanded, the particles will slow down. But with light, that's not the right way to think about it. Or maybe it is. So with light, you can think of it as a particle, but you can also think of it as a wave. And as this wave travels, it gets stretched. And the stretching just makes it less energetic. Yeah. And less energy, in our words, is also cooler.
Okay.
Yeah.
Sorry?
Sorry?
With a little point. Have you ever heard of the case of the car whizzing by, it's like, with a horn?
Yeah.
That's basically the kind of shift you get.
Yeah.
It's really way sound and light.
Unfortunately, we don't have any more time for questions, but Jielai will be sticking around for a few minutes if you'd like to ask her anything personally. So let's thank her again.